July 17, 1981. Kansas City, Missouri. Just after 7 in the evening, a hotel atrium filled with people for a weekly tea dance became the site of the deadliest structural collapse in United States history. Two suspended walkways, on the second and fourth floors of the Hyatt Regency, gave way and fell into the crowded lobby below. 114 people were killed. 216 more were injured. This was not the result of an earthquake, a storm, or an act of sabotage. It was the outcome of a single connection detail that was changed during construction and never sent back for engineering review. To understand how a hotel atrium became a mass casualty site, you have to start with the design on paper, months before any concrete was poured or any rod was hung. The original design called for a single continuous hanger rod. This rod was meant to run from the atrium roof, down through a box beam supporting the fourth-floor walkway, and continue further down to the second-floor walkway. In this configuration, each walkway's connection point carried only its own share of the structural load. Even in that original form, the connection was already operating close to the limits allowed by code. There was little to no margin for error built into the system as designed. That detail matters, because it means the structure had almost no reserve capacity to absorb any additional load if something about the construction changed. Nothing about the finished building suggested the danger inside it. The atrium was open, dramatic, and full of people that evening, walking across and beneath walkways that appeared, structurally, complete and sound. What no one dancing in that lobby could see was that the path the load was supposed to take through those hanger rods had been altered during construction, in a decision made away from the original engineering drawings. The rest of this story is about that alteration, who made it, who was supposed to check it, and why that check never happened before 114 people died. The failure began not with a mistake in the original design, but with a change proposed after that design was already set. During construction, the fabricator responsible for building the connection put forward an alternative to the single continuous rod. Instead of one rod running the full distance from the roof through the fourth-floor box beam down to the second floor, the fabricator proposed splitting the run into two separate rods. One rod would go from the roof down to the fourth-floor walkway. A second, independent rod would then run from the fourth-floor walkway down to the second-floor walkway. On the surface, this looks like a minor fabrication convenience, a simpler way to build the same connection. But the two configurations are not structurally equivalent. In the original single-rod design, the fourth-floor connection only had to bear the load of the fourth-floor walkway itself, because the rod continued past it to independently support the second floor further down. In the fabricator's two-rod version, the fourth-floor box beam connection now had to carry its own load, plus the entire weight being transferred up from the second-floor rod attached beneath it. Instead of splitting the load between two connections, as the original design intended, the new configuration effectively doubled the load being carried at that single fourth-floor connection point. This was the critical structural shift. A connection that was already close to the limits allowed by code under the original design was now being asked, under the revised design, to carry roughly twice that load. This change did not happen in isolation. It happened because a proposal made by the fabricator, a party focused on constructability and building the connection, moved forward into the finished structure. The step missing between that proposal and construction was a thorough rear-review by the engineer of record. The engineer of record, Jack D. Gillum of GCE International, did not thoroughly rear-review the fabricator's connection redesign before it was built. Whatever process existed for catching a change like this, one that fundamentally altered how load traveled through a life-safety connection, did not function as intended in this instance. The walkways were built to the revised, two-rod configuration. The building opened, and the connection now carrying double its originally intended load sat in place, holding up a walkway that would eventually be filled with dancers, waiters, and hotel guests on a Friday evening. At the center of this disaster is not a single miscalculation, but a breakdown in the review process that exists specifically to catch changes like this one. The original design was already operating close to the limits allowed by code, which meant that the margin for any deviation was thin to begin with. A design like that depends on a strict discipline. Any proposed change to how the connection carries its load has to go back through the engineer of record for scrutiny, not just a general sign-off on intent, but a specific check of the numbers behind the new configuration. That did not happen here. The engineer of record did not thoroughly re-review the fabricator's connection redesign before it was built. This is the structural equivalent of a decision being made lower down a chain of approvals than it should have been. The fabricator's proposal to split the single rod into two independent rods was, from a construction standpoint, a reasonable-looking simplification. But it was a decision about how load moves through a structure, and that kind of decision belongs with the engineer of record, not with the party fabricating the steel. When that boundary blurred, and the check did not occur with the rigor the situation demanded, a change that doubled the load on an already tight connection went from proposal to built reality without anyone confirming the connection could actually bear it. The investigation into what happened was conducted by the National Bureau of Standards, the federal agency that would later become NIST. Their investigation traced the collapse back to this exact sequence, a redesign that changed how load was distributed and a review process that did not catch it. The consequences for the parties involved were severe but specific. GCE International and the responsible engineers lost their professional engineering licenses. That is a professional and civil consequence, a determination that the standard of care required in reviewing structural changes had not been met. But a federal grand jury, convened in 1985, declined to indict anyone criminally. There was no finding of criminal intent, no verdict of deliberate wrongdoing, only a documented failure of process, a review step that should have happened and did not, at the one point in the entire project where it mattered most. On July 17, 1981, the atrium of the Hyatt Regency was hosting its weekly tea dance, a popular evening event that drew large crowds of guests and local residents into the open, multi-story lobby space. The walkways above were not incidental architecture. They were a gathering point, a place where people stood, walked, and watched the dance floor below. The second and fourth floor walkways collapsed onto the lobby, falling directly into the crowd gathered beneath them. 114 people were killed. 216 more were injured. At the time, and for decades since, this has stood as the deadliest structural collapse in United States history. Behind those two numbers is the reality that this failure occurred at the exact moment and place where the building was most full of people, during a social event specifically designed to bring a crowd into that atrium space. The connection that failed was not a hidden structural element in an unoccupied mechanical room. It was directly above a public gathering. The scale of casualties reflects that timing as much as it reflects the structural failure itself. In the aftermath, the disaster drew intense scrutiny from the press, in a city where the hotel and its collapse became the defining local story of the era. The Kansas City Star's coverage of the disaster and its causes won the Pulitzer Prize, a recognition of the depth of reporting into how a modern hotel, opened not long before, could fail so catastrophically and so publicly. That coverage helped ensure that the causes of the collapse, the fabricator's redesign, the missed review, the doubled load on a connection already near its limit, became part of the public record and part of the engineering profession's own reckoning with what had happened. For the families of the 114 people killed and the 216 injured, the technical explanation of hanger rods and box beam connections does not undo what was lost on an ordinary Friday evening at a hotel dance. But that technical explanation is also the reason their loss produced lasting change. The investigation by the National Bureau of Standards did not stop at identifying what broke. It identified why the process that should have prevented it broke down first, and that distinction is what shaped everything that came after. The Hyatt Regency walkway collapse did not change engineering practice because the physics involved were new or mysterious. Engineers had long understood how load travels through a hanger rod and a box beam connection. What changed was the profession's understanding of where responsibility has to sit when a design is altered after approval. The fabricator's proposal to split one continuous rod into two independent rods was a change to the structural load path, not a construction detail, and treating it as the latter is what allowed it to go unreviewed. The collapse fundamentally changed engineering practice nationwide, particularly around one specific requirement. The engineer of record must thoroughly review and approve any fabricator-proposed changes to structural connection design, not simply sign off on the overall design intent and assume the details will follow. That distinction between approving an idea and verifying a specific engineered change is the direct legacy of what happened in that atrium. GCE International and the responsible engineers lost their professional engineering licenses, a consequence aimed squarely at the review failure the National Bureau of Standards identified. No one was criminally indicted, but the profession's own licensing bodies drew a clear line. The standard of care required a specific, thorough check of this exact kind of change, and that check did not happen. The building industry did not need a new theory of structural mechanics after 1981. It needed a stricter boundary around who is allowed to finalize a change to a life safety connection, and a clearer expectation that a fabricator's convenience is never sufficient justification for a redesign to proceed without the engineer of record's direct, detailed sign-off. The National Bureau of Standards investigation and the Pulitzer Prize-winning reporting from the Kansas City Star that followed it ensured that this specific causal chain, a proposed change, a missed review, a doubled load on a connection already near its limit, became one of the most studied failures in American structural engineering. It remains a reference point not because the mathematics were exotic, but because the process failure at its center, a redesign built without being rechecked, is a risk that exists on every construction project where changes are proposed after the drawings are finalized. That is the lasting weight of July 17, 1981. A reminder that the review step skipped under time and construction pressure is often the one step a design has no margin left to survive without.